Ah, probability. Thank you. Thank you. All right, probability. We're doing that one now. So the ideas that we're going to talk about basic probability ideas, then we're going to talk about formulas, and then we're going to talk about tree diagrams. So let's get started with some basic probability. Something I think most everyone knew before they even took AP Stats. Probability is always between 0 and 1. All the probabilities added together for a given scenario must sum to 1. And every probability ever, this is my philosophy of probability. It's the number of ways to be successful over the number of ways to do it in general. That's every probability question, somehow, some way. More probability ideas. Probability has no memories. It does not remember what happened in the last trial. You flip 10 heads in a row. The probability the next one is a heads, still 1/2. When two events are mutually exclusive, so there's your vocab right there, mutually exclusive, that means they can't happen at the same time. Remember this symbol right here, that means and. So the probability that A and B occur is 0 if they're mutually exclusive. Some more basic probability ideas. I know I'm kind of going fast, but dependent events are events whose outcomes change based on the outcome of the other. So if I draw a card out of a deck, say I draw the King of Hearts, there's one less king, one less heart in the deck, one less card in the deck. So the next card is dependent on the previous card. Interdependent events do not affect one another. So, I don't know, maybe raining in Spain versus whether or not I eat cheese tomorrow, right? Those probably aren't going to affect each other. Mutually exclusive events are not independent. So the example that I always use is event A is the light is on. Event B, the light is off. Those events are mutually exclusive. They cannot happen at the same time. They are not independent because if A happens, I know that B didn't happen. If the light is on, the light is not off. There are two main ways to check mathematically for independence. You can use either one, just depending on what information you have. You can find the probability of A times B, the probability of A times the probability of B, and see if that's equal to the probability of A and B. Because when events are independent, they should be. Also, this is the definition, right? The probability of A given B is equal to the probability of A. So that basically means B didn't matter. If B happens, it does not affect the outcome of A. Either of those will work. It just depends on what you have is how you will determine what you do. I'm stumbling a lot over my words in this video. I hope that you get over it. Among registered voters of Franklin Township are the events is a male and is registered for party Y independent. So I'm going to go with this. I'm going to say probability of male given party Y. And I want to know, is that equal to, actually let's just do it this way. And then we'll find the probability of a male. So male given Y. So that means I only care about if they're in party Y. 48 out of 168 are male. The probability of male in general is 200 out of 500. As a decimal, 48 out of 168 is approximately 0.286. And this is 0.40. Are those numbers the same? No, they are not. That means these events are not independent. Boom, FRQ'd. All right, formulas. So the first one, the sum rule. This is a formula that's given to you. You don't have to memorize it, but I have it written there for you. It's the probability of A or B. Remember, that's or. the probability of A or B is the probability of A plus the probability of B minus the probability that both occur. The reason you have to subtract the probability that they both occur is because A and B is in this one, A and B is in this one. That means you've double counted it. So you have to subtract one of the copies. The general multiplication rule is the probability of A and B is equal to the probability of A times the probability of B given A. That formula is given to you as well. An experiment has three mutually exclusive outcomes, A, B, and C. If the probability of A is 0.12 and the probability of B is 0.61 and the probability of C is 0.27, which of the following must be true? Okay, first thing that's really important, three mutually exclusive outcomes. So these are mutually exclusive, A, B, and C. Only one of them can happen at a time. The first one says A and C are independent. Absolutely not. Mutually exclusive means specifically not independent. The probability of A and B is equal to 0. That is the definition of mutually exclusive. I'm happy about that one. The probability of B or C is the probability of B plus the probability of C. Well, if I look back, that's not quite what that formula says, right? What the formula says is the probability of B or C is equal to the probability of B plus the probability of C minus the probability of B and C. Don't B and C are mutually exclusive. So this is 0, so that goes away. This doesn't say divide by 0. Don't try and tell people that I told you to divide by 0 because it didn't happen. Okay, so that means that this is in fact true since they're mutually exclusive. All right, more formulas. The conditional probability rule. This is just really a manipulation of the general multiplication rule. This is the formula you're actually given. I lied a second ago. This is what you're given. You're not given this one. No, you're not given that. But if I take this formula and I multiply both sides by P of A, I get the other formula. So that's what you're definitely given. To find conditional probabilities, you do a joint or an AND probability over a single event, a simple event. Remember, the way we always do the probability of at least one is 1 minus the probability of none, because those events are complements. Tree diagrams, those are our friends. We love tree diagrams. We go outcome 1, outcome 2. And then there's something else. So we'll say A1, A2. And this could be A1 and A2, right? So that lets us map things out. And then if I multiply down the branches, I get AND probabilities. So the probability of outcome 1 and outcome A1, you would just multiply the probabilities down the branches. And that would happen all the way down through that way. So that's really useful. Tree diagrams are helpful. They make hard things easier. We're at examples. This is nothing but examples now, so get ready to do some problems. Complex, I pulled up my sleeves for this because, you know, writing with an iPad pencil is really difficult. A complex electronic device contains 3 components, A, B, and C. The probabilities of failure for each component in any one year are 0.01, 0.03, and 0.04 respectively. If any one component fails, the device will fail. If the components fail independently of one another, what is the probability the device will not fail? Oh my goodness, that's a lot. All right, so if any component fails, the device will fail. So the probability of failure is 0.01, 0.03, 0.04. I want to not fail though. So the probability of not failing that's 0.01 or 0.99. Sorry, it's the complement. Probability of B not failing is 0.97. Probability of C not failing is 0.96. Since I want this to not fail, and they're independent, I should just be able to multiply. Remember, independent events, to get AND, you just multiply. So it should just be 0.99 times 0.97 times 0.96, which is 0.9 0.99 times 0.97 times 0.96. And that's 0.92. In a certain school, 17% of the students are enrolled in a psychology course, 28% are enrolled in a foreign language course, and 32% are enrolled in either a psychology course or a foreign language course, or both. What is the probability that a student chosen at random from this school will be enrolled in both a foreign language course and psychology? So I want the probability of F and P, right? So foreign language and psychology. So the way we usually do that is through multiplication. However, they didn't give us very much information because they didn't give us that these events are independent, and they didn't give us that these events are, we didn't get their conditional probabilities, right? I feel like I'm doing a makeup tutorial. This is my white iPad pencil. See, it's a very good color. Okay, anyway, so we're going to have to use a different formula. There is another formula, though. Remember, the formula F or P, or FUP, as you may say, is the probability of foreign language plus the probability of psychology minus the probability of both, right? So I know this value, I know this value, and I know this value, so I can algebra that out. So F or P is 0.32. Foreign language is 0.28. And psychology is 0.17, minus the one I'm missing. So if I do the algebra on that, this is my algebra noise. I get the probability of foreign language and psychology is equal to 0.13. Yeah, that's it. So again, ordinarily when we do an AND probability, we're trying to do multiplication. But if we're doing multiplication, we need either the events to be independent or we need to know their conditional probabilities. We didn't have that, so we had to turn to some other formula. The probability that a new microwave oven will stop working in less than 2 years is 0.05. The probability that a new microwave oven is damaged during delivery and stops working is in less than 2 years is 0.04. The probability that a new microwave oven is damaged during delivery is 0.10. Given that a new microwave oven is damaged during delivery, what's the probability it stops working? So we want the probability that it stops working given that it's been damaged. Well, there's a formula for that. It's the probability that it stops working and is damaged divided by the probability that it's damaged. The probability that it stops working and is damaged, that's given right here, it's 0.04. The probability that it's damaged, right here, 0.10, which is 0.40. A company manufactures model rockets that require igniters to launch. Once an igniter is used to launch a rocket, the igniter cannot be reused. Sometimes an igniter fails to operate correctly, and the rocket does not launch. The company estimates that the overall failure rate, defined as the percent of all igniters that fail to operate correctly, is 15%. A company engineer develops a new igniter called the superigniter, with the intent of lowering the failure rate. To test the performance of the superigniters, the engineer uses the following process. Step 1. One superigniter is selected at random and used in a rocket. Step 2. If the rocket launches, another superigniter is selected at random and used in a rocket. Step 2 is repeated until the process stops. The process stops when a superigniter fails to correctly operate or 32 superigniters have successfully launched rockets, whichever comes first. Assume that superigniter failures are independent. Given that the first 30 superigniters successfully launch rockets, what's the probability the first failure occurs on the 31st or the 32nd superigniter tested if the failure rate of the superigniters is 15%? Apparently I cut that part of the problem off. Good thing I remembered it. All right, so given that the first 30 superigniters launched, I don't care. They're independent, right? This right here, independence. That means it doesn't matter what happened. Basically, I just want to know, will the first one, 31st, launch? Because if the 31st succeeds, we're going to launch a 30-second. If the 31st fails, we're going to stop right there. All right, so the probability that the 31st succeeds is 0.85. The probability that the 31st fails is 0.15. Now, the probability that the 32nd succeeds, so we're going down this branch now. We're trying to get more probability. The 32nd succeeds, it should be the same probability because they're independent. So that one's 0.85, and this is 0.15. I want the first failure to be on the 31st or on the 32nd. So the first failure being on the 31st, that's 0.15. The first failure being on the 32nd is 0.85 times 0.15, right? Because the 31st has to succeed for me to ever get to the 32nd. So it's going to be 0.15 plus 0.85 times 0.15. So remember, we multiply down the branches when we do these tree diagrams. So that is going to be hang on, relax, 0.2775. Isn't probability fun? 90% of the people who have a particular disease will have a positive result on a given diagnostic test. 90% of the people who do not have the disease will have a negative result. If 5% of a certain population has the disease, what percent of the population would test positive? So I'm just looking for the probability of positive, right? Okay, well, there are two ways that you can get a positive result. You can go probability of positive given that you can have a positive result and you actually have the disease. You could have a positive result and not have the disease. All right, so those are kind of what you can do. So what we need to do is we need to find the probability of those two things. The probability of positive and disease, probability of positive and not disease. I like doing tree diagrams, so I'm going to do one. So I'm going to say diseased and not diseased. It says that 5% of a certain population has the disease, so probability of that is equal to 0.05. Probability of that is 0.95. Now, of the diseased people, it says 90% who have a particular disease will test positive. So the probability of positive for them is equal to 0.90. The probability of negative then would be 0.10. For these not diseased people, it says 90% who do not have the disease will get a negative result. So for them, the probability of negative is 0.10. The probability of positive is 0.90. I need positive diseased people, and I need positive not diseased people. Oh, I missed the number. So I'm going to do 0.05 times 0.90 plus 0.95 times 0.90. And if I add those up, I should just get 0.90. Interestingly enough. That's a coincidence. Don't just trust it. It wasn't just 90 because. Don't. I'm watching you. I believe this is the last one. It is. This is the last one. A police officer is using a radar device to check motorist speeds. Prior to beginning the speed check, the officer estimates that 40% of motorists will be driving more than 5 miles per hour over the speed limit. Assuming the police officer's estimate is correct, what is the probability that among 4 randomly selected motorists, the officer will find at least one motorist driving more than 5 miles per hour over the speed limit? Okay, I see that word at least one. So I'm going to find the probability. I'm going to do 1 minus the probability of none. So I want to find the probability that the first is not 5 miles over. And second, not 5 miles. Oh, Janet's MacBook is back. Etc. Right? So these should be independent, right? It's reasonable to assume that motorists on a highway are driving independently of each other, at least as far as their speed goes. So I just need to find the probability that the first is not, times the probability that the second is not, times etc. Right? So that's going to be 1 minus 0.60 times 0.60 times 0.60 times 0.60. Now I know what you're thinking. Where did all these 0.60s come from? It says 40% will be driving more than 5 miles per hour over, so 60% should not be. So if I do that in the calculator, I get 0.874, 0.8704. And just like that, the probability ended.